In this video, we are going to talk about the net change theorem. And so first we're going to state what this theorem says. And so the net change theorem says the integral, I should say definite integral, the definite integral of a rate of change is the net change in the quantity's value. And typically we write this as the integral from a to b of capital F of x, f prime of x dx equals f of b minus f of a. Now note, this equation we've just written down is just the second part of the fundamental theorem of calculus, so it's not really anything new. But what the net change theorem is telling us is basically that an definite integral is going to tell us the net change, or how much a quantity changed over time, like the net overall change. Like if you have something increasing and decreasing at the same time, this tells us the net amount that it changed by. This has a lot of uses in the natural sciences as well as the social sciences. We're just going to look at some examples of where this shows up to give you an idea of how to use this formula, but it's really just the fundamental theorem of calculus part 2. So first, we're going to look at the following example. We're going to let f of t, which equals 100, t plus 20 meters cubed per hour, be the rate at which water flows into a reservoir at time t. The initial amount of water in the reservoir at time t equals 0 is 2,000 meters cubed. And we want to find the total amount of water in the reservoir at time t equals 10 hours. So we want to find the total amount of water in the reservoir at t equals 10 hours. And so what we're going to do here is we are going to figure out the net change and then add on how much there already was. And so this 2,000 is how much we started with, but our integral is just going to tell us how much we changed by. And so it's not actually going to take into account the initial part, and so we have to add on the initial part after the fact. And so what we're going to do here is the total amount is going to be 2,000 plus the integral from 0 to 10 of the rate of change, which was 100t plus 20. And so this is our initial amount. And this piece right here is our net change. So this is telling us over 10 hours how much did the water level change. Now, it could have gone up, it could have gone down. This formula only goes up, so hopefully it's obvious it went up. But it's possible that water could have been going out as well, and so this could be a negative number as well. It's kind of like the idea of how you have area above the curve and below the curve. You can get a negative net change. Maybe water was leaving faster than it was coming in, so overall amount could be lower. That's not the case here, but it certainly could be the case. And so we need to compute our integral. So we have the integral from 0 to 10 of 100 t plus 20. So this gives us 100 t squared over 2 plus 20 t, going from 0 to 10. So we have 50 t squared plus 20t. We're going from 0 to 10, so we're going to plug in our bounds. So we have 50 times 10 squared plus 20 times 10 minus 50 times 0 squared plus 20 times 0. Hopefully it's clear to you this second part is going to be 0 because we have 50 times 0 plus 20 times 0. So we're going to have 50 times 100 plus 200. So this is going to be 5,000 plus 200. So we get 5,200. And then our units are meters cubed. To figure out units, you consider what the original units were in. So they were in miles cubed per hour. And then t was in hours. And so just kind of like how we basically multiply by hours. So you can think of this as in the miles cubed per hour, which it is. And this is in hours. And so the overall units, you multiply them together to get the miles cubed. Or meters cubed, it's not miles. So we get 5,200 meters cubed. But that's not how much, that's how much we changed by. So that's our net change here, that's 5,200. But we have to consider the initial amount as well. And the initial amount was given by the 2,000. And so our total amount of water is going to be 2,000 plus our 5,200, which is 7,200 meters cubed. And so we consider both our net change as well as the initial amount that we had. Okay? So another example of this, and all these examples are going to feel at least somewhat similar. It's all based around this idea of the net change in something. And so a population of some bacteria in a petri dish grows at a rate according to the function g of t equals 200 times 2 to the t, where t is measured in hours. The initial population is 1,000. So we start out with 1,000 bacteria. We want to know what is the total population after 5 hours. Okay, so we want to figure out what is our total population of bacteria after 5 hours. And so first we want to figure out the net change in population, which will be the integral from 0 to 5 of our rate of change, which was 200 times t to the 2 to the t dt. And so this will give us our net change. And as a reminder, the antiderivative of 2 to the t is going to be 2 to the t divided by ln of 2. So this is going to give us 200 times 2 to the t divided by ln of 2, going from 0 to 5. And so we need to compute this number. So this is 200 times, we have 2 to the 5th divided by ln of 2, minus 200 times 2 to the 0 divided by ln of 2, So we have 200 times 2 to the 5th is 32. So 32 divided by ln of 2 minus 200 times 2 to the 0 is just 1. So divided by ln of 2. So this is going to give us 6,400 divided by ln of 2 minus 200 divided by ln of 2, which is 6,200 divided by ln of 2. But now this number we just computed, 6,200 divided by ln of 2, that is the net change. And so this is the number of bacteria that have grown in the dish in those 5 hours. But we started with 1,000 bacteria. And so the total population is going to be 1,000 plus 6,200 divided by ln of 2, which this is approximately 9,945 bacteria. That is rounded. It's actually 9,944.71 is more accurate, but we rounded up the nearest bacteria. Okay, so now let's look at another example. Now this next example is going to be a little bit more complicated than those first two, but it points out an important principle. And so a particle moves along a line so that its velocity at time t is v of t equals t squared minus t minus 6. And we're going to do two things here. So first, we want to find the displacement of the particle during the time interval 1 less than equal to t less than equal to 4. Okay, so we want to figure out the displacement of the particle during the time interval. Now, you may not actually remember what displacement means. If you haven't had physics, you probably don't. So just as a reminder, displacement is the net change in position. Okay, so displacement is measuring the net change in position. So it doesn't measure all the distance that you go, it just measures how far are you from where you started. So like if you started right here, and then you did some like weird path like this and ended right here, the displacement only considers this piece right here. That's the displacement. It doesn't consider all the weird loops that you might have done beforehand. Okay, and so we did talk about this once before. I'm just reminding you of it again. And so since it's the net change in position, well, we just want to take the antiderivative, or the definite integral, of the velocity, because velocity is the derivative of position. And so we take the integral from 1 to 4 of the velocity function. So we go from 1 to 4. The velocity function is t squared minus t minus 6. So that's what we need to take the antiderivative of. And so we're going to have t cubed divided by 3 minus t squared divided by 2 minus 6t from 1 to 4. And then we plug things in. So we're going to have 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus, plugging in 1, we have 1 cubed over 3 minus 1 squared over 2 minus 6. So this gives us 64 over 3 minus 16 over 2 minus 24. minus 1/3 minus 1/2 minus, minus 6. Okay, and so we want to simplify this. If you just simplify this overall, you end up getting negative 9/2. I'm just going to kind of skip to the answer. And so if you actually simplify it, you get out negative 9/2. And so this is the displacement. And I didn't tell us units, but these are all in meters. So this is in meters per hour. And so our units here would be in meters. So now what this tells us is we got a negative number out. So this means the particle moved 4.5 meters to the left. Okay, so that was its overall change. So in other words, if we started right here, it did a bunch of stuff, and it ended up all the way over here, and this distance right here is 4.5 meters. And so we've gone 4.5 meters to the left of where we started, because we assume right is the positive direction. And so the negative is just telling us we moved to the left rather than to the right. Okay. So now we want to ask a slightly different question. So now we want to find the distance traveled during the time period 1 less than or equal to t less than or equal to 4. Okay, so now we care about the distance that we traveled. So instead of just caring about like how far the net changes, we actually care about like all the stuff we're doing in the middle. And so rather than measuring what we just barely did, we have like this curve that's doing something like this, and we just measured this distance right here, but now we want to actually know like the whole length of this path. Okay, so we want to have the whole length of the path. We've done something like this before. You may or may not remember what we did. What we did is we took the position function, and then we looked at when we were moving in the positive direction, when we were moving in the negative direction, and like pieced them together to figure out the total distance. And that's basically what we're going to do here as well. But the way we're actually going to phrase it is slightly different, even though it does amount to doing largely the same thing. So as a reminder, our velocity function is equal to t squared minus t minus 6. And that factors as t minus 3 times t minus 2. And we factored it because we want to know when are we moving forward, when are we moving backwards. Okay, so we want to know when this is positive and negative. Okay, so in general, we have the following formula. So in general, the integral from 1 to 4 of the absolute value of v of t dt is the total position. Okay. I hinted at this briefly when we talked about area, talking about net area versus total area. Taking the absolute value forces everything to be positive. And so any place that we would have been going backwards, the absolute value makes us go forwards. And so basically what we're doing here is we're taking our curve that we have up here, and we're basically just straightening it all out. So instead of going backwards and forwards, we're just saying we're just going to straighten the whole thing out, and we go all the way over here. Okay, so instead of having all the back and forward motion, we're just basically taking the end and pulling it out, kind of like a string that you had curved on the ground. We're just kind of pulling it out by the absolute value. We're treating all the backwards directions now going forwards as well. Okay, and we did this before when we did absolute value to figure out position by looking when we went backwards and forwards. So the question becomes, how do you take the integral of an absolute value function? And that's what we're going to do. So we're taking the integral from 1 to 4 of the absolute value of t squared minus t minus 6. Well, as it turns out, this is actually something that we are pretty well equipped to handle, as we've done something similar to this before. So remember what absolute value actually means. The absolute value function is a piecewise function. So this function is going to be equal to t squared minus t minus 6 if t squared minus t minus 6 is greater than or equal to 0. It's equal to negative t squared minus t minus 6 if t squared minus t minus 6 is less than 0. And so we just need to figure out when are we greater than 0, when are we less than 0, and then we're going to split up the bounds of integration based on this fact. And we have done this before when we did the integral of a piecewise function. And so we're doing the same thing here. We're just splitting it up in pieces based on which function we're using in this piecewise equation. It just occurred to me that I factored this wrong. And so this is going to be t minus 3 times t plus 2, which is going to be relevant as we're going to use that equation to figure out when we're greater than 0 and when we're less than 0. And so looking at this, we have v of t equals t squared minus t minus 6, which equals t minus 3 times t plus 2. And so we want to figure out when we're positive and negative. But on the interval 1 to 4, t plus 2 is always positive. So we're really looking at t minus 3. And so looking at t minus 3, well, on the interval from 1 to 3, t minus 3 is going to be less than or equal to 0. Because we're going to have something less than 3 minus 3. So we're less than 0 on 1 to 3. And then from 3 to 4, we're going to have that t minus 3 is greater than or equal to 0. So 3 is our breaking point. It's the point where we have to change equations. And so we have here the integral from 1 to 4 of the absolute value of t squared minus t minus 6. We're going to split it at 3. And now for the first piece here, from 1 to 3, we're negative for that entire distance. And so we're going to stick a negative in front of everything. And so we're going to have the integral from 1 to 3 of negative t squared minus t minus 6 dt. Then plus, and on 3 to 4, we are positive, so we just have t squared minus t minus 6 from 3 to 4. And now we take the antiderivative of everything. Well, actually, let's multiply it out. First, we get 1 to 3, negative t squared plus t plus 6. Just multiplying our negative in. And then the second one doesn't get changed at all. Now, taking antiderivatives, we get negative t cubed over 3 plus t squared over 2 plus 6t from 1 to 3. And plus t cubed over 3 minus t squared over 2 minus 6t from 3 to 4. And so we want to plug things in. And so plugging in for the first one, we have negative 3 cubed over 3 plus 3 squared over 2 plus 6 times 3. Minus, and plugging in 1, we have negative 1 cubed over 3 plus 1 over 2 plus 6. Then we add on to that what we get when we plug in 4. So we have 4 cubed over 3 minus 4 squared over 2 plus, minus 6 times 4. And then minus 3 cubed over 3 minus 3 squared over 2 minus 6 times 3. Okay. And then just kind of skipping to the end. I didn't do all the intermediate steps here. But if you compute all of these, you end up getting 61 over 6 meters, which is approximately 10.17 meters. And so what we found here is that the total distance we traveled is 61 over 6 meters, even though we ended up traveling 4.5 meters backwards. So that means when we're straightening out this line, as we talked about a second ago, that straightening out of the line, this whole length here is 61 over 6 meters, even though we went backwards 4.5 meters. That means that we had some cancelization happening because we were going both backwards and forwards. But this allows us to get the total distance that we traveled.